Hi everyone, today let's solve the problem number 199 binary tree right side view. So what the question states here, we are given the root of the binary tree. See here, clearly you can clearly see here root. We have been given the root of the binary tree, right? So we have to imagine standing on the right side of the tree. Let's imagine, see here, they have showed an arrow mark here, right? So just give me a second here, 1 second. So this has to be, yeah, this has to be visible. This is fine. Now you can clearly see here we have to imagine we are standing on the right side of the tree from top to bottom, right? So from top to bottom, right? So we have to return the values of the nodes. You can see we have to return the value of the nodes that we can see. In simple words, we have to return the last node of each level when viewing from the edge. We have to return last node of the each level when viewing from the edge. We are standing at the right side. First we will view 1, right? So top to bottom we are going. Next we will view this one 3. Again from top to bottom we are going. From 3 we will see 4. From 1 we will see 3. From 3 we will see 4. And then from 4 we will see the last one, level order. From 1 we will see 5. We are seeing this one, uh, top to bottom means we have to imagine standing on the right side of the tree from top to bottom. See, from the right side means we are considering entire right side, not the left side. Top to bottom we are going. So this one is one. From one we will see 3 first. See, from one we will see 3 first. From 3 we will see 4. So this will be 1, 3, 4. From 4 we will see, we cannot see 2. From 4 we cannot see 2. We have already at the bottom. Some from 4 we can see next depth, or which is at the level, which is at the same level basically, right? So it will be 5. So the output has to be 1 2 4 5. 1 2 4 5. At this level 3 you can ask, we can see 2 as well. We cannot see 4. We are going from top to bottom. We are going from top to bottom, not the level. Only if this one, what do we call, bottom value is not present and the same level, and at the same level the other value is present, then only we'll be considering the value. So this I had to mention this one strictly. So let me remove this one. So here from 1, this one 3. From 3 we can see 4. This will be 1 3 4. So again, so from 3 we are not considering 2 at the same level, because we have to go with the depth from top to bottom. They have strictly mentioned in the question. So from after 3, either we can consider one value, 4 or 2. So here 2 we cannot consider. 2 we cannot consider. This will be 1 3 4 and 5. This will be 1 3 4 and 5. So let's consider the second example. Let's consider the second example here. So just give me a second here. Yeah, we have 1 3 1, this one, what do we call, uh, yeah, we have 1 2, basically 1 2 3 4, null. Again for 3 also we have null, and finally we have 5. Finally we have 5. So see here, we are standing at the right side part of the tree. So this will be 1 3 1 3, right? So for 3, the depth, next depth we have to go. Next step, we have already considered 3. From 1 and 3 we have already considered 3. So the same level we cannot consider, right? So we will, the next step, the next value is 4. We will see 4, right? So we will see 4. The next value we'll consider is 5. We'll consider is 5. So this will be 1 3 4 5. So this will be 1 3 4 5. We are left with one more example here. So this one I got confused, man. So this one I got confused, sorry. We shouldn't consider the same level value. So this is not 1 3 4 5. This is top to bottom 1 3 and 3 to 4. I really got confused here, sorry. So this one has to be 1 comma 3 comma 4. So 1 comma 3 comma 4, not 1 comma 3 comma 5. So sorry, I explained this one wrong. So 5 we shouldn't consider basically, right? So only one value we have to consider, that is from top to bottom. So 1 3 4. If we have another value 6, suppose you consider 6 here, and we don't have any value here, suppose this is null and null, then we can consider 6. Then we can consider 6. So for this one we have to consider only 1 3 4. Sorry, I really got confused here. So this has to be 1 3 4, right? So we are done with the first and second example. Same goes with the second example, 1 3, then this one followed by 4, and this one followed by 5. We cannot consider the same level, this thing, right? So we can either go with the BFS or the DFS, right? So for DFS, we have to write the extra code because we have to check every depth and this thing. For BFS, we can just uh, consider the value, the right value at each level, the right value at each level. And then if the right value is not present, then we can just go with the left value, the next level left value, right? So that we can do, that we can directly do with the BFS. So it's better to go with the BFS rather than the DFS. The code would be lengthier if we consider DFS, right? So they have given first two examples we have considered. You can consider in the same way for the this one, same way for the third and fourth example. So here this is one, so null, left side is null, the right side is 3. So we have only two values. So top to bottom will go, so the output will be 1 comma 3 quite obviously for the third one, right? So that's what they have given. For the fourth one, we have empty root here. It's empty tree basically, right? So we just have to return the empty array for this one output. So I hope this part is completely clear, man, right? So let's discuss the approach followed by the complexities, and then let's write the code. First, let's discuss the approach. Let's consider the first this one, same this thing, right? So we have already discussed this one. We have to know this one, man. We have to know this one. So we will be going with the just give me a second here, 1 second. Yeah, we will be going with the BFS. We will be going with the BFS. You can also go with the DFS, but the code will be little lengthier. So I'll just go with this. Problem is basically designed to be solved with BFS. So let's go with the BFS rather than DFS for this particular problem. Let's go with the BFS, level order traversal. We'll be going with the level order traversal basically, right? So we have 1, 2, 3, 1 this first level and this second level, and the binary tree indexing starts from 0. So this is 0, the level 1, and this is level 2. This is fine. So here what we will do, first we will consider the level 0. Here we have the node 1, rightmost node is, this is node 1, right? So here let's go with 1, let's go with 1. Rightmost node is 1, we'll go with 1. And for the level 1, we have 2 comma 3. We have this one, 2 and 3 at the level 1, right? So what is the rightmost node is 3. We are considering the rightmost node as the person is standing at, we have to imagine the person standing at the right side, and we have to go from top to bottom. That's what they have given in the question. That's what they have given in the question. Out of 2 comma 3, the rightmost node is 3 here. Rightmost node is 3, right? So top to bottom we are going 1, 3 followed by 3. So we have to consider the rightmost node nothing but 3. Same will do for the level 2 as well. Here we have the values 5, 5 comma 4, 5 comma 4. We have to consider the rightmost node and the top to bottom 3 which connects the 4. So we have to we have to consider the value 4 here. So this is nothing but 4, 1, 3 and 4 we got. So this is nothing but rightmost value. This is nothing but rightmost value for 1. So let me write this one. Let me consider braces, and let me consider this one, rightmost value for the level 0, for the level 0, for the level 1 and for the level 2. So this is 1, 3 and 4 uh, respectively. So this one we need to return in the form of output, nothing but 1, 3 and 4, 1, 3 and 4. So I hope this part is completely clear. So we are going with a pure BFS here, BFS level order traversal, right? So you can just try it out in the same way for the example 2. I insist you to try out the same thing for the example 2. So I'll just get the output 1, 3, 4, 5, this one for the this one second example, right? So I insist you to try out for the example 2. You'll understand the question better, man. In my opinion, you'll understand the question better. So here in this case, we have the output 1, 3, 4. This will be the output, which is equivalent to the output that they have given for the example 1 in the question. So our approach works absolutely correct in this case. So let's quickly discuss the complexities part as well. So what will be the time complexity here? The time complexity would be big of big of n, not logarithmic n. So the time complexity would be big of n. The time complexity would be big of n, because we will be visiting each node exactly once. We will be visiting each node exactly once. So the time complexity would be big of n. So what would be the space complexity here? The space complexity would be big of n as well. The space complexity would be big of n as well. Why the space complexity here is big of n? Because for the queue storing nodes level by level. So we will be making use of the queue as we are going with the BFS level order traversal, right? So we'll be making use of the queue rather than stack. If we would have went with DFS, we would have made use of the iteration. with iterative DFS instead of the recursive DFS, right? So we would have went with a stack, right? So instead we are going with the BFS level order traversal. So we'll be making use of the queue here. In this case, for the queue storing nodes level by level, it will take the overall space complexity would be big of n, right? So big of n. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n respectively, right? So let me delete this one. As we are completely familiar with the approach as well as the complexities, we are good to write the code. Let's start writing the code. Let's start writing the code. So the first part here is we have to store the rightmost node of each level. We have to store the rightmost node of the each level. For that one, we'll be making use of the, for storing purpose, we'll be making use of the array list. So I'll just go with the list. So here we'll be going with the, we have to store the rightmost node of the each level. So we'll be making use of the array list. So list of, so here we have the integer, we have the integers, right? So we'll be considering integer variable name would be we are storing, I'll just go with the result. You can just go with the answer result, res ans anything. So let me go with array list. So this is fine. Just the syntax. Next, if the tree is empty, we have to return the empty list, nothing but the base case. This is the base case. If the tree is empty, we have to return the empty list. The fourth example that they've given in the question. This one I'm speaking of, man. Right. So let's go with the base case. Here, if the tree is empty, we have to return the empty list. Nothing but here, if root equals null, then we have to return result. Then we have to return result. So this is fine. So the next step is we have to we will be going with a queue as we had discussed earlier. I said we'll be going with a queue. Uh, Before some time I said that we'll be going with a queue as we are going with the BFS level order traversal, right? So let's go with the queue for level order traversal. So I'll just go with queue here, queue. So this one will be tree node. So the variable name, this one has to be capital T, man. This is fine. The variable name I'll consider here queue itself, queue. Well, so this one will be new link list as we have made it, as we are making use of the queue. You can just go with the array dq as well. We can just go with the array dq as well. So I'll just go with the this one, linked list, pure queue, right? So we are standard queue method basically. So we are going with the queue for the level order traversal. So now let's start the BFS from root. Now let's start the BFS from root. So here this has to be queue dot offer. Offer means we are starting, right? So we have to start the DFS from the BFS from the root. So first queue shouldn't be empty. Queue should consist of some elements, right? So for that we'll write the while loop. So here this one queue dot is empty. Q dot is empty. So this is fine. Within the while loop, what shall we do? We have to go with the number of nodes at the current level, particular level, right? So we are going with the in the first example that we considered, we had three levels: level 0, level 1, and level 2. So now we have to go with the number of nodes at the particular level or the current level. So here I'll just go with int level size, and let me initialize this one to q dot size. So this is fine, q dot size. So the next step is let's go with the for loop here. Let's go with the iteration part or the for loop. So we have to get the next node in the level, right? So we have to get the next node in the same level. For that one we have to consider all the levels and we have to get the next node in the same level. For that purpose we are going with the iteration part here. So I'll just go with for int uh this one will be I equals 0, I less than, this will be level size, and this one will be I plus plus. So this is fine. Within the for loop, what we will do, we have to get the next node in the level. So I'll just go with the tree node. Let me consider the variable node equals q dot poll. This is fine. I hope this part is completely fine, man. So let's write the simple if condition now. If I, it's level size minus 1, this is fine. So within the if condition, if it's the last node in this particular level, we have to add that one to the result, nothing but right side of the each level, means rightmost node of the each level. We are adding that one to the result, nothing but it will be the last node. It will be the last node in the particular level. The rightmost node will be the last node at the particular level, right? Except the root node. Except the root, um, rightmost node will be the last node at the particular level, right? So if only node is present, that is at the left itself, then we have to add that one also, right? uh, that one also, that also we have to consider accordingly with the question. So here I can write that one in this form. If I equals, we are comparing level size minus 1, then we have to add that one to the, if it is last node in the level, then we have to add that one to the result, nothing but I'll just go with the operation add here. So we have to add the value, right? So this will be node dot value. So this is fine. Let me come out of this one if condition. Now we have to add the left child to the queue and add the right child to the queue as well. Add the left and right child to the queue. Let's write the simple if condition, two if conditions here. So this will be node dot left not equal to null. Then this will be queue dot offer. This one will be node dot left. This is fine. Let me give control C. This will be control V. This will be, instead of left, I'll just go with right. So this is fine. Q dot offer. This will be node dot right instead. So this is fine. Let me come out of this one entirely. We are done with the, almost we are done with the code. The last part is we have to return all the rightmost nodes that we have collected. All the rightmost nodes that we have collected so far, right? Nothing but we have to return a result in simple terms, right? So this is fine. Return result. So let me format the code and let me hit the submit button. So I should have hit the run button, man. So yeah, this is fine. I have directly hit the this one submit button. So all the test cases are getting passed, right? So all the test cases are getting passed. So our code works absolutely correct for all the test cases, right? So I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.